Hi there. This video is going to walk through a quick discussion about the different ways that we have been talking about our internal energy of our system. So we have seen that we can discuss the internal energy in terms of the first law of thermodynamics, which is kind of that change in heat or change in work that affects the internal energy of our system. And we've also talked about it in terms of our differential equation of state, where we've looked at the change in internal energy with changes in volume and temperature. Okay, so we're just going to take a minute to see if we can satisfy ourselves that these two ways of looking at internal energy are equivalent. Okay, so let's take a look at our first law version of how our system energy can change. So let's focus just on the heat part of our equation. So we know there's a work component in there as well, but let's just focus on the heat. So let's say we have essentially an isochoric system. So hopefully you recall from our previous discussions that isochoric means constant volume. Okay, so that essentially eliminates our discussions of work, since there's going to be no change in volume, which means we have no change in our PV work, as we call it. Okay, so we can just focus on the heat into or out of our system. Okay, so one thing to think about is as we change the heat into or out of our system, we're also changing the temperature of our system. So as heat goes into our system, so if we have this situation, then we're going to raise the temperature of our system. Okay, you've all experienced that in the laboratory. As you put something on a hot plate or under a Bunsen burner, right, the temperature starts to go up. Same idea, if we have heat leaving our system, we're cooling our system, so the temperature of our system should correspondingly go down in relation to the removal of that heat from the system. All right, so clearly heat, or Q, is directly related to our temperature. Okay, so we can write that as such. Okay, so we know there's some direct relationship between Q and T. So as we change our the heat into or out of our system, we're also going to correspondingly change the temperature. So we'll make that a dt. All right, so there is another factor that's going to fit in here. Obviously, not every substance is going to have the same response to the same input or output of heat from the system. So when you heat up a beaker of water, that temperature change is going to be different than if you were heating up the same mass of, let's say, copper or aluminum or mercury. Okay, so every substance has its own kind of characteristic response to the input of heat into it, and that we've already seen is what we call our heat capacity. Okay, so every substance, it's going to have its own characteristic heat capacity associated with it. Okay, so we can measure heat capacities for different substances. So if you know that you put in, let's say, 210 joules of heat, okay, and then let's say you had a 10K temperature change associated with that, then we're able to say that our heat capacity for that particular system is 21 joules per Kelvin. Okay, so nice easy relationship here between our heat, our temperature, and our heat capacity for a substance. Okay, so we've encountered CV before. We've encountered that heat capacity term before. Over here, when we were talking about our differential equation of state for our internal energy. So we also know that CV represents the change in internal energy as a function of temperature at constant volume. So again, still in that isochoric system, right, with a constant volume. So CV represents also the change in internal energy as a function of temperature, as well as giving us a measure of the change in heat as a function of temperature. Okay, so you might be asking yourself, well, how do we know for sure that these are the same CVs that we're talking about? How do we know they're the same heat capacities, same quantities? Well, let's start by looking at our differential equation of state that we associated with this figure. So remember when we talked about the state space, we had our differential equation of state that looked like this. We have du equals cv dt plus pi t dv. Okay. And then if we want a similar differential over here, right, remember we had du is equal to dq, which is our change in heat, and dw, which is the change in work. Okay, so remember we are talking about an isochoric system here, okay, which means we've got constant volume. So what that means is this term is going to disappear, okay? Remember that's our constant volume. So that dV is going to be 0, all right? And then we also know that this term is going to be 0 for essentially the same reason. There's no change in volume, so there's no expansion or compression that's going to change that pressure that we talked about earlier that relates to the work of our system. Okay, so now we have a situation where we know dq is equal to cv dt, okay, and then we have cv equals dq dt. Okay, so then we also know that du equals dq. All right, so we could rewrite that as du dt. Okay, and because we are at constant volume again, we can just make that added notation there, and that looks an awful lot like our expression for CV over here. Okay, now again, this is all kind of justified under an isochoric system. It makes it nice and easy to see that relationship between the two CVs that we are working with, but this is just to show you that we do in fact have essentially the same quantity that we're dealing with in these two systems, or I should say these two representations of a system. So just to complete our derivation over here, so we know that that's at constant volume, so this is the linking of our first law approach to looking at the internal energy to our differential equation of state way of looking at our internal energy, and we see that we end up with the same components that arise from that treatment. So we end up with the same CV here as we do over here. So all is well with the world. Everything is consistent. This is just another look at how everything that we've been talking about with internal energy kind of ties together in a consistent way. So hope that was helpful. And keep working with your state spaces and your first law calculations, and you'll get a good grasp of how this internal energy of our system can be manipulated with changes in heat or work, or also with changes in temperature and volume. So remember, all of those quantities are related to one another. So heat and temperature are related, and our work and our volume are related to one another. Okay, that's it.